Dear students, in this session I would like to discuss methods of population estimates and projections. Population data are needed for variety of purposes. These data are provided by censuses which is conducted once in 10 years. The data are required even during intercensal, post-censal, even for the future years by the planners, policymaker, researchers, businessmen and other people. Therefore, population estimate find a important place in the provision of population data in the intercensal, post-censal, even for future years. Here, population estimate in between any two census years may be termed as intercensal estimate, while population estimate at any point of time since the last census till date may be termed as post-censal estimate. Likewise, population estimate at any point of time from now on in the future years can be termed as population projections or future estimates. Intercensal estimate is a kind of interpolation method, and the post-censal is an extrapolation. In the intercensal, post-censal and for future years can be done by applying variety of methods. The methodology may vary according to the unit of projection, say national or subnational. The types of methods for population projection can be of two types, namely number one is mathematical methods and number two is component method. Mathematical methods are very simple, usually requiring a simple mathematical exercise. Mathematical methods are methods of curve fitting to the observed or given data, and the estimate can be obtained. However, one must have to consider the following 3 points for applying mathematical methods. Number one is the functional form of the curve to be selected for population estimates or projection, the characteristics of the curve and method of fitting, assumptions in the mathematical methods. The important assumption is that the past trend will continue in the future also. That means the rate of growth in the past is assumed to be constant, or the rate of growth for the future also. Data requirements. Normally, population estimate and the population projection mathematical methods requires population totals for number of years or number of points of time. However, certain growth functions like linear, geometric, exponential requires 2 points of time data from which the important parameter, that is the growth rate, is calculated, and the growth rate is substituted in the equation in order to get the estimate or population projection. Therefore, for calculation or computation of growth rate under these 3 growth functions, namely linear, geometric and exponential, we need data for 2 points of time. At the same time, for these 3 growth function, we may also can fit best fit curve, and from that population estimate and projection can be made. In order to fit best fit curve using these 3 growth functions, require at least 3 points of time data or more points of time data. Further, the growth functions like modified exponential, Gombert's and logistic law of population growth requires a minimum of 3 points of time data or in multiples of 3. Then only this growth function can be fitted to get a best fit curve. Mathematical functions for population estimate and population projections. The simplest one among the mathematical method is the linear growth function, which is given by Pt equal to P0 plus Bt or Pt equal to P0 into 1 plus Rt, where Pt is the population at time t, that is the population to be estimated. P0 is the population at base year. B is the annual average increase that can be calculated by dividing the difference between the population at these 2 points of time by the total number of years. T is the number of years between the base year 0 and t, that is the t is the year for which the estimate is to be made. R is the rate of growth, which can be calculated by dividing total increase during the period 0 and 1 divided by mid period total population. After getting the value of R, substitute the value of R in the equation and get the estimates or projected population for the year for which it is required. The second important growth curve is the geometric law of population, which is given by Pt equal to P0 into 1 plus R power t, and the second degree curve also can be used in the place of geometric law, which is given by the equation Pt equal to A plus Bt plus Ct square, where Pt is the population at time t, that is the population to be estimated. P0 is the population at the base year. T is the total number of years between the period 0 and t. R is the rate of growth, which is equal to tth root of P1 by P0 minus 1. Once the value of R is obtained, substitute the value in the equation and get the population estimate or population projection, as the case may be. In the equation of second degree curve, which is given by Pt equal to A plus Bt plus Ct square, in which A, B and C are constants that are to be estimated from the given population totals, normally requiring at least 3 points of time data, and the best fit curve is obtained. Then the value of t is substituted in the best fit curve already obtained and estimate or project the values. Both the geometric and exponential form assumes a compounding process in the growth of population. The third important population growth model is Pt equal to P0 e power Rt, where Pt is the population at the time t, that is the population to be estimated. P0 is the population at base year. T is the number of years between the period 0 and t. R is the rate of growth, which can be calculated by log P1 minus P0 divided by T log E. E is the mathematical constant which is 2.718. Since population growth is a compounding process, in the initial stage of population expansion, it is better to apply either exponential or geometric growth models for population estimate and projection in order to arrive at best results. However, for 1 year estimate, linear law or linear growth model would yield better results because it is only considering 1 year interval for the estimate. Fitting the modified exponential, Gombert's and the logistic law of population growth, we need population total for at least 3 points of time or multiples of 3 points of time. The modified exponential function is given by Pt equal to a plus b into c power t. The Gombert's law is given by Pt equal to a b power c power t, and the logistic law says Pt equal to k by 1 minus e power a plus bt, where a, b and c are constants to be estimated for a given population totals P1, P2 etc. Pn, where n is equal to 3 or multiples of 3. Pt is the population at a time t, that is the population to be estimated. A, b and c are constants to be estimated from the given population total, and the best fit curve is obtained. By substituting the value of t in the best fit curve, one can get the estimated or projected population totals. E is the mathematical constant, and k in the case of logistic law is the maximum population size that can be attained by the country. The application of method is explained in the diagram. The procedure is as follows. Divide the given series of data into 3 sets equal number in each, and the number of values in each set is called m. Let S1, S2 and S3 be the sum of the first m, second m and the last m. From the population totals, compute S1, S2, S3, D1, D2 and D1 by D2. Once these quantities are computed, then C, A and B are estimated from the equations already given 1, 2 and 3 in the population growth function equations, namely Pt equal to a plus b into c power t, that is modified exponential, Pt equal to a b power c power t, that is Gombert's law, and Pt equal to k by 1 minus e power a plus bt is the logistic law. Here it is important to note that the given series of data have to be used in the following form. For modified exponential function, use the data as given and obtain the parameters a, b and c, and substituting the value of t, one can get the population estimate and projected value for the year for which it is required. For the Gombert's law, first convert the given values into log values and then compute the parameters a, b and c and get back them as the original values by taking anti-logarithms. For the logistic law, convert the given values into reciprocals and obtain the parameters a, b and c, and then convert the parameters, that is a, b and c, reverting to original form by taking again reciprocals. The selection of appropriate curve requiring the knowledge of the finite differences is essential for understanding the properties of the curve. The guidelines for the selection of appropriate curve for the given data are: number 1, if the first differences of the function are nearly constant, fit a straight line or use a linear growth function. If the second differences are nearly constant, fit a second degree curve or geometric growth function. Thirdly, if the first differences of the logarithm of values are nearly constant, fit an exponential function. If the first difference tend to decrease by a constant percentage, then use a modified exponential form. And fifthly, if the second difference of the logarithms are nearly constant, fit an exponential parabola. Sixth point is, if the first differences of logarithms are changing by a constant percentage, use Gompertz law. And lastly, if the first differences of the reciprocals are changing nearly by constant percentage, use the logistic curve component method. In this procedure, each component of population change, namely fertility, mortality and migration, are projected separately and then combined to add to the total population to get the estimated or projected population. This method is an extension of the balance equation procedure to get the population total. The component method is a laborious process. It involves number of steps. Calculation procedure is also needing time and number of calculations are required. But the population projected would yield better results when compared to the results obtained from the mathematical methods of population estimates and projection. The population change between year t and t plus 1 can be broken into its components as pt plus 1 equal to pt plus b minus d plus im minus em, where pt plus 1 is the population projected or estimated, pt is the population at t years or base year, b is the total births during the period t and t plus 1, d is the total deaths during the period t and t plus 1, im minus em is the total net migrants during the period t and t plus 1. Under component method, population projection is done for males and females separately, because there are a lot of variations in the mortality rate for males and females in different ages. Data requirement for population projection under component method. Here, when compared to mathematical methods, component methods require number of data for its computation. Number 1, age sex distribution of population in the base year. Number 2, age specific mortality rate or lifetime survival ratios in the projection period for males and females separately. For the base year, estimates for the year for which a projection is to be made. Thirdly, estimates of fertility, that is any of the period fertility measures like GFR, ASFR or TFR or other relevant measures can be considered here. However, one has to careful in handling fertility measures and its variation in the future years, because fertility rates are affected by number of factors, and these factors have to be taken into consideration. Fourth data is migration. If migration is in large volume in the country, then we may have to consider migration as an important component for population projection. Otherwise, migration can be treated as zero, or we can assume that the effect of migration is zero. In the case of net migration, it is to be obtained for age sex group for the base year, and also estimated for figures for the year for which projection is to be made. The procedure under component method is given in the diagram, which gives the projection of female population for 10 years period. In the diagram, the column 1 refers to the age group of the population. The column 2 is the number of females in the base year are entered. Here the upper subscript represent the year and lower subscript represent starting age of the 5-yearly age group. Normally 5-yearly age group is adopted for population group projection under component method. In the third column, females in the 5-year age group, 5 years after the base year is entered. Female population is estimated by surviving the base population for 5 years. For surviving the population, life-table ratios relating to the 5-year period of 0 to 5. For example, F20 after 5 years equal to F15 at base year into survival ratio during the age interval 15 to 20 at the mid period. The column 4, the procedure adopted in the column 3 is repeated, treating the population in the column 3 as the base population for the projection for the next 5-year period. In the whole of the projection period, migration is treated as zero. The mathematical method is the simplest one, involves easy procedure, and it is only a mathematical exercise. But the selection of the curve or growth function is very important to suit the population under consideration. Component method is a laborious process, involves a number of procedure, and also the data under consideration for population estimate or projection under component method are many, and so the researcher has to handle the procedure as well as data in order to yield better results. On any account, component method is superior one when compared to the mathematical method. However, in the case of short period estimate or projection, mathematical method is considered to be useful and appropriate than the component method of population projection. Thank you very much.